Good evening everyone. I welcome you to the ninth problem solving session of NPTEL course Combinatorics. So today we'll be discussing few problems on graph theory and graph theory in particular on planar graphs and the Hall's theorem. Okay, so let's start. So first I want to recall what is Hall's marriage theorem. It's so before so first I'll recall Hall's marriage theorem. So before that, first we'll define what is a matching. Matching for a graph is, it is a set of edges and all these edges are pairwise disjoint. That means no two edges share a common vertex. So you see this is an example of a graph, and if we want to find a matching for a graph, we are basically looking for a set of edges which don't and no two edges should share a common vertex. So we can see in this graph, in these graphs, the three edges that are colored red form a matching for this graph, and similarly three edges which are colored green, they also form a matching for a graph. So this is what is called matching. Now Hall's theorem says that Hall's theorem basically gives us a condition for a bipartite graph when we can always guarantee a when Hall's theorem gives us a condition that guarantee that there will be a matching on a bipartite graph which is covering at least one of these sets. So it gives conditions, necessary and sufficient conditions for that. So our Hall's theorem says that first we start with G, which is a bipartite graph. Say first set is called, we call it X, and second set we call as Y. Then G has a matching that covers X. That means we are able to find set of edges and which is covering X. That means any vertex of X is present in one of the edges that we have selected. Then G will have a matching that covers X if and only if we consider any subset S of X, the order of neighborhood of S should be greater than equal to order of S. By neighborhood of S we means, so if we have just one vertex in our set S, by the neighborhood of X we mean all other vertices which are adjacent to it. And if we have multiple vertices in our set S, we are basically collecting all the vertices which are adjacent to at least one of the vertices in our set S. So we see the beauty of Hall's theorem comes from that this condition is kind of an obvious condition. That is, if we want to have a matching, this condition should be satisfied. But the beauty comes from the fact that this is also a necessary and sufficient condition, that if this condition is satisfied, we can always find a matching. So why I am saying that this is an obvious condition, we can see in this example. So suppose in this example, my set X is set of men and my set Y is a set of women, and there's an edge between a man and woman if a woman is interested in that particular man, and the problem is to find out a matching for women such that each woman can be matched with a man of her choice. So solving this problem is equivalent to find a matching for this graph. So now if we try to find a matching for this graph, we see we won't be able to find it due to the presence of these three women. So we see if we have these women W2, W3, W4, so in together they only, so if we construct this, look at the men that they prefer, it has just two men, M2 and M3. So if we want to create a matching that is covering X, so suppose we assign second man to the women 2 and third man to the women 3, there is no man left for the fourth woman. Therefore we see that this condition is kind of if we want to have a matching, this condition should be satisfied. But the Hall's theorem say that it is a necessary and sufficient condition. So in this graph we cannot this condition is not satisfied due to the presence of these three women. So this graph does not have a matching that cover X. But in this example, we can see if we check that this condition is satisfied and we also have a matching. We also have a matching that is covering the set of women. So this was Hall's theorem. So now let's solve some question. Our first question is that we are given a graph G which is K regular and bipartite. So we have basically, this is our set X with n vertices, V1, V2, Vn, and we have a set Y, with n vertices only, W2. So we are given a bipartite graph, XY bipartite graph, and order of X is same as order of Y, and the question order of X is same as Y, and we are also given that G is K regular. By K regularity, we means that degree of each vertex, that is degree of Vi, is equal to degree of Wi, which is equal to K. Now the question is, given these conditions, that is a bipartite graph in which both the sets have same number of vertices, and plus we are given that it is K regular, then we have to show that there is a matching that covers X. So previously, just now we discussed Hall's theorem, which gives us necessary and sufficient condition for finding a matching in a bipartite graph. So we see that if we want to show that this graph has a matching, it is enough to show that we need to check Hall's condition. So it is sufficient to show the Hall's condition. And what is the Hall's condition? If we start with any subset S, of X, say S is equal to some V1, Vk, Vj, then we have to show that order of neighborhood of S is greater than equal to J, because this is what is order S. So we need to show this, and the information that we have is that each vertex has degree K. So how can we use this information to show this? So first of all, so basically we need some condition, we need to show this condition. So we want to count the neighbors of S. So first is, let's count neighbors of S and allow repetition. That is, if you don't allow repetition, so if any two vertices Vi has same neighbor, then we are including it twice. So if we want to count number of S and we are allowing repetition, so how many neighbors are there? So we have J vertices and each vertex has degree K. Therefore, this will give us Jk neighbors, because degree of each Vi is K. Now secondly, let's count maximum number a neighbor Y can be repeated. So we see that since degree Y is equal to K, Y cannot be a neighbor of more than K VIs. Therefore, maximum number of Y can be repeated is, answer for 2 is K. And now if we want to see what are the total neighbors, so we can see that total neighbors is if we are allowing neighbors with repetition, and if we divide it by the maximum number of times it can be repeated. So this is the worst case scenario. This is the worst case scenario, that is when each of the neighbor is coming in, when each of the neighbor is repeated k times. So we see that neighborhood of S will have at least these many vertices. And what is this term? This term is just J. So we get the false condition. So we get false condition, that means false condition hold. Hence a k regular bipartite graph has a matching covering X. So this was one of the application of marriage Hall theorem, Hall's marriage theorem. Now next question. So our next question says that we are given a k cross n Latin rectangle. That means we have k rows and n columns, and we have to show that any k cross n Latin rectangle can be completed into n cross n Latin square. So first of all, what is a Latin rectangle and what is a Latin square? So Latin square of degree n, that is n cross n Latin square, is basically a n cross n grid, and we have n different symbols, and each row is allowed to have at least, each row and each column are allowed to have exact one symbol. Any symbol should appear exactly once in each row or column. So if you have played Sudoku, if you have solved Sudoku anytime, Sudoku is an example of a 9 cross 9 Latin square, where symbols are just number 1 to 9. And what is a Latin k cross n rectangle? So in Latin k cross n rectangle, we are given k rows, n columns and n symbols. And here also in each row and each column, a symbol is allowed to appear at most once. So here we have at most one, because since if k is less than n, all symbols cannot appear in a single column. So now we have to show that if we are given a Latin k cross n rectangle, how can we complete it into Latin n cross n square? So these are some example of Latin square. This is an example of a Latin square, 3 cross 3 square, and you can see each column and each row have ABC in exactly one, ABC are taking exactly one position in each row and column. So A are appearing here, which are different. B is also appearing different, and C is also appearing different. So this is a 3 cross 3 Latin square. And now here also, if you have 4 symbols, this is a 2 cross 4 Latin rectangle. So suppose this is a Latin rectangle, and we have to show that this can be completed into a Latin square. So we'll prove this by induction on K. By this I mean that first we'll show that K cross N Latin rectangle can be extended to K plus 1 cross N Latin rectangle. That is, we'll extend one row at a time. Cross, and if we show this, we are done, because then we'll have to apply this n minus k times. So it is sufficient to show this. So what do we need to do? Given a k plus 1, given a k cross n Latin rectangle to extend it to k plus 1 cross n Latin rectangle, what we have to do? We have to basically assign a symbol to each column C1 till Cn, such that it should satisfy two conditions. First of all, since we have to construct a Latin rectangle, so each symbol, assign a symbol Si to each column Ci. So first, the symbol that we are assigning, symbol Si, it should not be all. So since each column can have one symbol at most one times, this symbol Si can't be already appearing in Ci. And secondly, we are not allowed to have we are not even allowed to have two same symbols in one row. So all these S1, S2 and Sn should be distinct. So now if I have stated this problem in this sense, so think for a minute, think for some time, how using using Hall's theorem how can we show this now when this problem is reduced to doing this, can we show this problem using Hall's theorem? Think for some time. Okay. So what we are doing, so we have to assign what we have to do, we have to assign a symbol Si to each column Ci, and symbol Ci can't be already appearing in Ci, and S1, S2 till Sn, these all symbols should be distinct. So what we are doing, this is equivalent to choosing a system of distinct representatives. Each representative denoting the symbol that we should assign. So this is equivalent to choosing a system of distinct representative, and this representative is what? It is denoting the symbol that we should assign to a column. So from what kind of sets we are choosing? So each distinct representative is giving us a symbol for a column. So we are choosing system of distinct representatives from A1, AN. Each set is for each column. And what are the elements of AI? AI is the set of all elements that can be added to symbol, that can be added to column Ci. And what are these symbols? These are basically all those symbols Sj, such that Sj is already not appearing in Ci. So we see that our problem is now reduced to choosing a system of distinct representative from this n tuple of sets Ai. And now we have seen in class that choosing a system of distinct representative is equivalent to finding a matching in appropriate bipartite graph. So here how our bipartite graph will look like. So this is further equivalent to finding a matching in XY bipartite graph covering X, where what is our X? So we have to find a symbol for each column, and what is Y? It is the, so we have to find a matching and we are assigning a symbol. So Y should be S1 Sn, and when, where X is this, and when Ci and Sj is an H, so Ci is joined to Sj. So what are the possible choices for column Ci? Ci Sj is an H when Sj is belonging to the symbol Ai. That is, this is a symbol which is already not appearing in this. So in this Latin rectangle case, so what we are basically doing, so we are constructing four sets A1, A2, A3, A4, and A1 is basically the symbols not appearing in, A1 are the symbols not appearing the column 1. So what are the symbols here? Plus and divide. And similarly the symbols for A2 here is multiplication, divide. For A3 circle, multiplication, and for A4 we have plus and circle. So these are the sets Ai. And now if you want to construct a bipartite graph, what we are doing? So our problem is to either select system of distinct representatives SDR from this, or find a matching for which is equivalent to saying SDR from this, or matching, perfect matching, basically which is covering all the vertex, that is a perfect matching from this following graph. Plus, and the other symbol is multiplication. So what is the so when they are edges, A1. So this is the graph for C1. C2 is the multiplication. Oh, sorry, this is just one symbol. So we see that our graph looks like this, and C3 is 0 plus, and C4 is attached to plus and 0. So now we have to find a perfect matching. So in this example we can easily find a perfect matching, I think. So if we are going with this with this, okay, this with this, this with this, this with this, then this is a perfect matching. So what are we doing? We are adding plus here, divide here, multiplication here, and 0. So we have extended it to a k+1 rectangle. So now in this case we are seeing this perfect matching is existing. But why it is existing here? In the general case. So our question, it is equivalent to finding a matching for XY bipartite graph where Ci Si is an L with this. So to show existence of matching, we need to check Hall's condition. And in this previous example we see that what is, like, if you observe, like, think what is, so is this relating to any previous problem we have done? That is there any commonality, is there any special property of this bipartite graph? So we can see each of these vertices have degree 2. So it is a 2 regular graph. And we have in the previous question showed that if we have a regular bipartite graph, matching always exists. So if we can show that this is also in general case it also is a regular graph, we are done. We need to check Hall condition from last question. It is sufficient to show that G is regular. And is it so? So if we want to compute degree of each Ci, so Ci is connected to basically degree Ci, sorry. Ci is basically connected to all those symbols which are symbols not appearing in Ci. So how many symbols are not appearing in Ci? So this is a k cross n rectangle, and each symbol is appearing at most once. So we see that n minus k symbols are not appearing in each column. Therefore degree of Ci is this. And similarly degree of each symbol is it is basically counting the columns not having Si. So now it has k rows, so k rows and n column, so every row has a symbol Si. So if every row has a symbol Si and there are k rows, so k columns also have a symbol Si. So how many columns does not have symbol Si? N minus k. And so we see that it is a n minus k regular graph. So we are done. So this was also an application of Hall's marriage theorem. Okay. Now next, let's discuss some things about some problems on planar graph. So before that, let's recall what is a planar graph. Planar graph is a graph that can be embedded, planar graph is a graph that can be embedded on a surface such that the vertices form distinct points of the surface, and edges are simple curves between these points, and no two curves are allowed to intersect each other. So this is what is a planar graph. Now you see in this example, if we see the standard representation of K4, so we have assigned so if our surface is my screen, then we see to these 4 points we have assigned vertices are becoming these 4 points of this screen, and the edges are this. But these two edges are intersecting each other. So this is not a planar representation of it. But we see that if a graph has, if we give this graph a different representation, that is, if V3 is shifted to the interior. So if we have this V1, V2, V4, and if we shift V3, so we have this curve also, and if we shift this V3 to the interior, then this is also K4, and no two edges have a intersection. So we see that K4 is a planar curve. So the point is that a planar curve may have a representation which have edges that are intersecting, but that does not imply that that curve cannot be planar. So for a graph to be planar, we require one embedding. One embedding even if we can find one embedding where no two edges are intersecting, then we are done. So this is a planar graph. Now for planar graphs, we have nice identities. That is, if we add vertices and faces, number of vertices and number of faces, and subtract the number of edges, we always get 2. And we have seen the proof of this result also in classes. So this is just an two examples which are showing that this identity is indeed holding. So but like these examples, so I just need you, one should be careful that when one is counting faces, it should also count so this is a face, this is a face, but this face, outside face, should also be counted. So we see here that this has 5 vertices, 3 faces, 6 edges, and if we do the calculation, we see that Euler identity holds. And in this K3 also, we have 2 faces, not just one, interior and exterior. Exterior is also counted as a face. So we have 2 faces, 3 vertices, 3 edges, and Euler identity hold. And using Euler identity and some and some calculations, modification, we saw in the lectures that if we have a connected planar graph, we have a upper bound on number of edges. That is, total number of edges should always be less than equal to 3 times number of vertices minus 6. And this upper bound can be made better in case of a connected bipartite graph. So if we have a connected bipartite planar graph, then we can say that we have this upper bound, that number of edges should always be less than equal to 2 times number of vertices minus 4. So this was a brief recall of planar graph and some of the results on planar graph. Now let's solve some problems. So our first question is that we have to show that there exists a planar graph of n vertices with 3n minus 6 edges. So order of vertices is n and order of edges is 3n minus 6. So why we have selected 3n minus 6? We are showing, this will be my remark 3, this is my remark C, that if we show this, we are basically showing that upper bounds on number of edges for planar graph which we have, which was n edges, the upper bound was 3n minus 6, it cannot be improved because we actually have a planar graph with n vertices and these many edges. And similarly in question 2, we'll be showing that Kn2 is planar, and if Kn2 is the bipartite graph where one set has n vertices and other set has 2 vertices, and here also if we count the number of edges, they'll come out to be 2b minus 4. So if we showed these both 2 problems, we have shown that we are basically showing that remark C, that upper bounds on number of edges for planar and bipartite graph cannot be improved because we are able to give an example for when those upper bounds are being attained. And we can also, like, if we show these 2 problems, we are also getting two more nice observations. So in class we have seen that K33 is not planar, and I think you also have to prove this using Jordan curve theorem. So we have seen that K33 is not planar, and in second question we are showing that Kn2 is planar for all n. So if we see, so this is basically saying that Kmn is planar if and only if one of these m or n is less than equal to 2. So why is that? If one of this m or n is less than equal to 2, we get reduced to the case problem number 2, and for problem number 2 we have already shown that such thing is planar. If m or n is less than equal to 2, that means if one of these m or n is 2, then we are done. And if other thing is that one of the m or n is 1, and if one of the m or n is 1, then it is obvious. So we see that if m is less than equal to 2 or n is less than equal to 2, then we have that Kmn is planar. And we also have the converse. So converse basically we are showing that if Kmn is planar, then one of these has to be less than equal to 2. Why is this? Because if both of them are more than 2, if both mn are greater than 3, then k33 is a subgraph of that graph, and we have already shown that k33 is not planar. Therefore we get that kmn cannot be planar. So basically we have categorized all complete bipartite graphs which can be planar. And similarly for complete graphs and similarly we can also conclude it for complete graphs. So we, in the first example, we saw that k4 is planar, and in the one of the assignments problem from this week, we have to show that k5 is not, and we have proved it using, we have seen it its proof using that upper bound thing. So we get that if kn is planar, then it is planar only when n is less than 5. So we have these three nice remarks. So now let's solve first n2, which will imply these remarks. So first is that we have to show the existence of planar graph of n vertices with 3n minus 6 edges. So if n is equal to 2, n should be greater than equal to 3 also. Yeah, n is greater than equal to 3. So for n equal to 3, this we see that this is our planar graph. This is the planar graph with 3 edges, because it should be 3 into 3 minus 6, which is 3. For n equal to 4, we want a graph with 6 edges, and so we already have seen this also. This is k4. Now for n equal to 5, we have to do 3 into 5 minus 6, which is 9. So basically we have to add one more vertex and 3 more edges, and we are not allowed to have self intersection. So what is the obvious way to do this? Add a vertex at top and then add 3 edges. And similarly, so we see in this corresponding cases, we have to add 3 edges and one vertex. So in general also you see, so for n plus 1 we have this we need a graph of this many edges, and for n we have this edges. So their number of edges difference is 3. So at each stage keep on adding edges in above fashion. Hence because for each number you have to add 3 more edges, so hence we are done by induction. Okay. Now next question was, you have to show that kn2 is planar. So this is an obvious, I want you to try this question. You can, this is very simple, so you can think it before seeing the solution. You can think about it for some time, but the solution is basically this. So if you have these n vertices, first you make an x thing with n vertices, and now the second set has to have two vertices. So if I make my 2 vertices like this, there is no way I can avoid this self intersection, right? So what I do, I remove I put w2 on the top, then I won't have any self intersection. So this is the graph. So we have shown both the things, and so these two questions were fairly simple. Now let's come to the last problem. Okay, sorry, there's one more problem before that. So first we have to show, now the next question is, we have to show that every planar graph has a vertex of degree at most 5. So for a planar graph, we have the identity that number of edges is less than equal to 3 times number of vertices minus it was 6, right? Yes, 3v minus 6. So suppose we have n vertices, suppose order G equal to n. Let order G equal to n, and suppose this condition is not holding, that is degree Vi is greater than at most 5, so it is strictly greater than 5, which is same thing is saying that degree Vi is greater than equal to 6 for all I from 1 to n. So now if we sum all these degrees, we see that it is 6n, and here also from the how sum of all degrees, how do we relate it to number of edges? Each edge contributes 2 degree, therefore this is equal to 2 times number of edges. So we see that number of edges is 6n by 2, which is 3, and which is clearly this is 3n, which is clearly greater than 3n minus 6. But this was an upper bound for number of edges. This cannot happen, a contradiction. So we see there exists Vi of degree at most 5. Now the last problem. So now we have to so in the last week we discussed the sir discussed the coloring problem. He said that for a planar graph it is sufficient to have 4 colors to color any planar graph, and for the proof also he gave a brief history of what is. So for proof of 4 proof of 4 is maybe tricky, but we can see that we using elementary techniques we can show that 5 colors are sufficient. That is, chromatic number for any planar graph is less than equal to 5, or 5 colors are sufficient to color any planar graph. So by coloring, what we mean? Assign a color to each vertex. No 2 vertices which are adjacent can have same color. Okay, so we'll prove, so as we can, like if we have some theorem like this, like if we can't think of a direct way, the first guess is always to try using induction. Let's see if we can do it by that. So for n equal to 1, obvious, assume that result holds for k vertices. Proof by induction on number of vertices. Assume result hold for k vertices. Now we have to show assume that result hold for k vertices, that is G with k vertices, G planar, 5 colors are sufficient. Now proof for k plus 1 vertex. So from last question, we know there exists a vertex V whose degree is less than equal to 5. We just showed it. So we are doing induction. So basically we are trying to find a representative, find a vertex which we can remove, and then we can apply induction hypothesis, and we have to somehow relate 5 colors. And in the last question we have already shown that we'll have a vertex which will have degree at most 5. So let's try removing that vertex. So let G dash is equal to G minus V, that is remove V, edges adjacent to V, incident to V. So by induction, G dash can be colored by 5 vertices. So we just need to find an appropriate color for V, the vertex that we had removed, for V in G. So let's first get rid of some obvious cases. So if we have case 1, if degree V is less than 5, and case 2, degree V is equal to 5 but vertices have adjacent vertices have been colored by less than 5 colors. So in both cases, choose a color not being used, and you are done. So what is the remaining case? That degree of V is 5 and all neighbors of V have different color. So in this case what we do? So first let's draw a picture. So what a picture look like? So if this is vertex V, we have degree is 5. So, and each have different colors, say red, blue, green, gray, and black. So this is our case that we have a vertex V and all its neighbors have different colors. So now how do we do it? So what we do, we pick 2 alternating vertices. That is, they have just one vertex in between them. Any 2 vertices, say we are picking one with red color and picking the other vertex with green color. Now look at okay, let's go X. I'll be needing this space, so I'll so I'm just doing it here. Yeah, so what we are doing, yes, so if we are looking at subgraph of G, and which has edges connected to V1, V2, and each edge should be colored red or green. So we are considering subgraph of this. So in a way, what we are looking at, so we are looking at the edges coming out from, we are looking at the edges which are coming out from red and green, plus they should have color red or green. So suppose this is the diagram, and so we have to give a red or green color. Yeah, so we are looking at subgraph of this type, and similarly here, sorry, this is proper coloring, it should be red, this is given red, oh this is red, so this should be green, sorry, this is green, this is also, oh this is red, okay, let's so you get it what we are doing, right? So this is this. So here, so we are collecting all such things. We are looking at the subgraph. We are basically collecting all the edges connected by V1 and V2, and each edge has one endpoint green and other endpoint red. So we are looking at this graph. So now here also two things can happen. So they can, so these two branches, they can be connected by some edge, or the other cases they are not connected by an edge. So first case is that suppose there is no connection, that this is what, there is no connection. So first case is that branches from V1 and V2 are not connected. So they are they are connected by V, but they are not connected by any other path, are not connected besides this path, V1, red green branches also, not connected besides this path, V1, V2. So if this is so, we can see what we can do is, we choose one of these branches and swap the colors. So what we are doing, okay, we are basically just swapping the color of one of the branches. So yes, so we are giving, so all the vertices which were given a green color in the first branch, are given the red color, and the vertices, so we are swapping the colors basically. So we have something like this. So if we have this, we see that so sub branches from V1 and V2 are not connected beside this path. Swap colors from one of the branches. If you do so, then you see that both V1 and V2 have green color. Say branch coming from V1. Now both V1 and V2 have green color. So we can give red color to V, and we are done. So this was our case 1, basic sub case 1. Now sub case 2 is branches from V1 and V2 are connected non-trivially. So if we have the same diagram, yes, so this one was our diagram. So we have these branches, and now what we are saying that they are connected. They are connected, suppose, yes, they are connected like this. They are connected. So now you see, you can't always swap the colors. So from one of the branches, because the cycle might be odd, even, and so you cannot always guarantee that swapping color will help you. So now what you do, you repeat the same process with the one of the, so now this is a, so now since they are connected, you are getting a cycle. So if you consider a closed curve, so V1 V2 V1 V2, and this was suppose say V3 V4, at least so this cycle, the additional cycle separates V3 and V4. Both, we started with an alternating vertices, and since it is a planar graph, both V3 and V4 cannot lie in the interior, and by a construction also we see that. So this additional cycle separate V3 and V4. So repeat procedure in subcase 1. With V3 and V4. And if you see, if you will have some vertex, these are the additional some vertices. Now for V3 and V4 we'll always, for V3 and V4 for V3 and V4 we'll always end up in subcase 1. That is, branches from V3, V4 can't be connected without going through this path. Therefore, swap the colors in branching coming from V3 and we'll be done. So what we have to do, so if this was our case, what we are doing, we are looking at the branch coming from V3 and V4. We are looking at V3 and V4, and then we are swapping the colors. So by swapping colors we mean that we swap the colors, and now we see that this both V3 and V4 have the same color, so we can give blue color to our V, and we are done. So this was the last problem, that is, any planar graph can be colored by 5 colors. Okay, so that's it. Thank you.